Hello Math 126 students. In this video I'm going to talk about and review how to find error bounds for a Taylor polynomial when you are given an interval. So I already just made a video introducing my intentions here, but ultimately we're using this. Again, if you want to know where it's from, consult lecture, consult my previous video. Now I just like to use it. So the rule is find the next derivative, get an upper bound on the next derivative, and then replace. So I'd like to do a couple of those problems. If at any point you forget any of this, you can go to my materials page, click on, if you just want a quick summary, it's here. If you want a more detailed summary with a more step-by-step, that's here. Oh, I clicked on the wrong one. This one here. And it really breaks down. In general, you can find the absolute max by doing this, but in these problems you can do this. So this really breaks it down. Now you should also be getting some good tips as you do the homework. I think I will use the test prep, since I already have made that for you, to practice this, and then we'll end with maybe looking at some other old exams and then maybe glancing at the homework. So what are you trying to do for these questions? Ultimately, I'm talking about this question down here. So this question says, find the first Taylor polynomial. So g of 1 is the square root of 4, which is 2. G prime of x is 2x over 2 times the square root of 3 plus x squared. So g prime of 1 equals 1 over 2. And now we have our first Taylor polynomial. That's not what I wanted to talk about, but let's get ourselves there. It says estimate what the value of this would be. So unfortunately, I have to think a little bit about what would you have to plug in for x to make this 3.25. And I think you'd have to plug in x equals a half. Because if you plug in x equals half, you would get this. So that means t1 of a half is 2 plus a half. Half minus 1. 2 minus a fourth, 1.75. Okay, but the question was to use Taylor's inequality to get an estimate for how close this might be. So let's do it. So step 1, compute the next derivative. So we need the second derivative. And this is probably a harder problem than most because the derivative was a little bit harder to compute and simplify. A lot of the questions, especially in the homework, are not quite this complicated, but let's just go. We compute the derivative, the second derivative. I'm using the quotient rule. Denominator times the derivative of the numerator, which is 1, minus numerator times the derivative of the denominator, which is this, all over the denominator squared. And I think the real challenge here on this test was simplifying this, because we know we need to find a bound, and I don't know how we're going to find it unless we simplify a little bit. So I would multiply top and bottom by this square root. So I'm going to do a little bit of simplifying here. Just a general good rule of thumb is if you have a fraction inside of a fraction, multiply top and bottom by whatever that is. In this case, it's kind of nice because this times this is 3 plus x squared. And this is just x squared, because all you get, let's see if I can highlight what I'm seeing, all that's left here is this, and those two things cancel. And on the bottom you have this times this. So if this hadn't simplified, this problem wouldn't have been doable, but it does, and those cancel. So you do want to simplify, and like I said, this is probably one of the harder problems from an old test. But you want to simplify down small enough that you can tell, you can actually analyze it. So now our job is to figure out the biggest this can be on the interval they gave us. The biggest this can be is when the denominator is smallest. The denominator is smallest if I put a half right there. Okay, so there's a little bit of work that goes into that thinking. So this is going to be 3 over 3.25 to the 3/2. So that's the challenge. Now I did that quickly because I just thought about the fact that it was a fraction with a constant on top. It's going to be biggest when the denominator is smallest. So this could take longer. That's the one challenge, is to figure out when is this biggest. But the moment you have that, you're done, because then you can say the error is less than or equal to whatever this number is divided by 2 x minus 1 squared. That's Taylor's inequality. It was based at, sorry, was it based at 1? Yep, it was based at 1. And then we're going to plug in whatever we were, approximating at, which was at 1/2. And then we compute that number, and there's our answer. That's the process. If we look, see if I can show this real quick. Let's see, where is it at? And that was my intention. I realize not everyone's going through these test preps. I know you have other things to think about, but you can see where I'm working through this and getting this. Now, in the posted solution for that exam, the instructor may use simpler numbers. They might have replaced this with just a 3 on the bottom just to make it easier to write out. But this is correct. A larger answer would also be correct. Okay, let's do another one. Let's look at the next one. So this question said, give the second Taylor polynomial. So you had to plug in 1, which is going to be e to the 1, which is e. You're going to compute the first derivative, which is going to be 2x e to the x squared. And when you plug in 1, you get 2e. And then you're going to take the second derivative. And now I'm going to need a product rule. Derivative of the first times the second plus the derivative of the second times the first. That means f double prime of 1 is 2e plus 4e, so 6e. So the second Taylor polynomial is going to look like this. And we're going to put, let's change these colors. This is going to be e, this is going to be 2e, this is going to be 6e. Okay, give an upper bound for the error. Okay, so that question is asking us to do Taylor's inequality. So we need the third derivative. Oh no. So you're going to want to try to simplify. I mean, I probably would factor, but let's say I didn't realize I could factor. Let's just take the derivative right now. It's going to be 4x e to the x squared. That's this one. Plus 8x e to the x squared. That's, I'm doing the product rule on this. Plus the first term, so it's going to be 8x cubed e to the x. I got that by taking the derivative of this, which is 2x, and multiplying times that. And all together, this is going to be, let's see, I think there's an e to the x squared. So the challenge here is simplifying. I think I can take an x out. And what is left? I think here I'm just going to have 12. And here I'm going to have plus 8x squared. So if I was doing this, I would simplify even a little further. So why am I worrying so much about simplifying? Because I know that I have to give a bound. Okay, so now my one job, and this is kind of a challenge here. This is, like I said, I tried to find a couple that were a little hard. A lot of them you can tell right away what the bound is, but I need some number that I know is bigger than this. And the question is not asking you to find the best answer, because it's actually really impossible here. But if you're only plugging in a number between 0 and 2, there's a few things you can say. For example, I know that this is less than or equal to 2. So this is what we want you to do. Is if it was complicated, look at it in pieces. I know that this collectively is less than or equal to, if I plug in a 2 here, that's the biggest that's going to be. So if I plug in a 2 there, I'm going to get 8. I'm going to get 11 here, I think. This is going to be 8 plus 3. And then lastly, the biggest I can get here is a 2. So notice I didn't try to prove that my answer was right. Now, I suspect that is the maximum if I did more analysis, but the question doesn't ask me to do that. It just says, write down something that you know is bigger than this. Okay, I would write down this. So 88 e to the 4. So that's the sort of analysis we're doing. We're not asking you to be more precise than that because most of the time that's not possible. Then you're going to plug in. So you say, okay, the error, which is what this is less than or equal to m, and we just said m was going to be 88 e to the 4th, over 3 factorial, which is 6, x minus 1 to the 3, and then we're going to replace this with 2 or 1. And there's our answer. If the question is what's the smallest error, that's just a goofy. For a few years, people like to ask this. The answer is just 0, because the error would be 0 when that's 1. So this is the upper bound is what Taylor's inequality gives you. Okay, let's do one more of those and see. And I haven't been looking at the solutions. There we go. That's it. Let's do yet another and see what happens. And I'll switch to the other topic. Find the second Taylor polynomial for this. So we just plug in 0 and we get 0. We take the first derivative and we get 1 plus x times cosine plus sine. And then we take the second derivative, and it's going to be 1 plus x times negative sine. I'm doing the product rule. Plus 1 times cosine plus cosine. That's a derivative of this. The rest of this came from the product rule. Okay, so we're trying to plug in 0. So when I plug in 0 to the derivative, it looks like I get 1 times 1. So I get 1. When I plug in 0 here, I get 0 there, I get 2. So the second Taylor polynomial, we're based at 0 this time, is going to have a 0, 0, 1, 2. And I forgot the square. Given upper bound on the error. So once again, bad news is we need to compute the third derivative. So at this point, I would try to simplify. And these, like I said, these are some of the worst questions I've picked here from old tests. Just so, as I didn't want you to be, I wanted to show you examples of as bad as it can get. But the main challenge is simplifying. I know some people are scared of that, but you do want to simplify when you're trying to give a bound to make your life easier. So I need to compute the next derivative. The next derivative would be, okay, the first times the derivative of the second is cosine plus the derivative of the first, which is negative 1, times sine, and the derivative of this, which is negative 2 sine. And so we're getting negative 1 plus x cosine of x minus 3 sine of x. So the absolute value of this is this. I mean, we can include the plus, the minuses or not. It doesn't change the absolute value, so I'm going to write it without. And now it's a real challenge. If someone said, find the exact answer, meaning if you did a graph of this in a graphing calculator or online or on Desmos, the actual maximum, I don't know what it is. You know, it might be somewhere here. But I can find a bound that is maybe a little higher, but easy to find. And that's what we would like you to do on this. So if the question is just to give an upper bound and you see a cosine, just say, I know this is less than or equal to 1. I know this is less than or equal to 1. So we're allowing you to be slightly imprecise here. Because on this interval, one of these is actually a tight bound, 1. But for sine, it's much less than that. But you can make your life a lot easier. So, and I can say this is less than or equal to 0.01. So overall, this is all less than 0.1 times 1 plus 3. So this is all less than 4.01. That's the sort of analysis. We allow that for error bounds because it's too hard to find a precise error bound. And most of the time when you're doing an approximation, it wouldn't be possible to find a tight bound. Okay, so that's sort of weird for people, so I wanted to show you some examples like that. And most of the homework we can find tight bounds. Okay, so let's fill everything in now. So the Taylor's inequality says that the error, this thing, is less than or equal to m over, in this case we're doing this, so 3 factorial x minus 0 to the 3, and we're going to plug in 0.01 here to get one number over the whole region. Let's peek at my solutions there. Okay, so there is several examples where we go through that. Let's now take a peek at two things before I finish this video. The other two will be a little bit shorter, but this one has... So in your homework, that's what these questions are about. They give you an interval. They ask you for an error bound. So all you're going to do in this one is compute the second derivative. You're just going to practice this game, the second derivative. So these sorts of ones should be pretty fast. There's a negative there, but when you put absolute values, that's gone. And then you ask, what's the biggest this can be in this interval, which in this case we can do it quickly. It's biggest when the denominator is smallest, so it's going to be biggest when we put in a negative a half here. That ends up being 4 because it's 1 over 1/2 squared. And then you write 4 over 2 factorial x minus 0 squared, and then you replace this with a 1/2, and you get a half. So this is our answer. Now, if this number was bigger than a half, it would also have been correct, but since that was the only one, that's what we picked. So same thing like with this one, if you want to get this answer, I suspect after you do a couple derivatives, so the first derivative is 10 cosine of 5x, the second derivative is negative 50 sine of 5x, and if I put absolute values around it, this is less than or equal to 50. I suspect that's what they used to get this number. Is that the tightest bound? No, I think on this interval, sine doesn't make it all the way up to 1. But that's okay. If you got an answer smaller than this, that doesn't mean you're wrong, but it does mean this is correct. It is true that the error is less than this if you prove that the error was less than this. Okay. That's the idea of that. I think I'll leave that, but hopefully you now know, if you're looking at old exams, old finals, and you get to page 7, and if I just click on a random one, I haven't prepared this, and you get to the second to last page, and it gives you a function, hopefully you can immediately give the Taylor polynomial. This is a question that's about, given the error, find the bound. So I'll make that in my next video. Let's look at another one. This question says, give an upper bound for the error. This one looks kind of like it might be kind of messy, but you know what you need to do. You need to basically make it to the fourth derivative. Ooh, that's kind of messy, but it must simplify as you go. Okay, that's that problem. So you kind of know what's coming. Let's look at this one. Give an upper bound on the error. So you're going to need the third derivative of whatever they gave us, and then you're going to find a bound. Okay, I think I'll leave that.